Hello everybody, welcome to the course VLSI Design Flow RTL to GDS. This is lecture number 6. In this lecture, we will be continuing with the overview of VLSI Design Flow. In the previous lecture, we had looked into RTL to GDS flow and we had said that we can divide the RTL to GDS flow into two major portions. The first part is the logic synthesis part and the second part is the physical design. In the previous lecture, we had looked into the logic synthesis part, and in today's lecture, we will be looking into the physical design part. Now, let us first understand what is a physical design. So, physical design is the process by which a design in the form of a netlist is converted to an equivalent design in the form of a layout, and this layout typically we represent in terms of GDS or the geometrical patterns that we want to have on the mask that will be further used in fabricating that IC. So, let us look into the framework of or the inputs and outputs for a physical design. So, the major inputs for physical design are, the first one is the netlist. The netlist is basically the design that we have obtained after logic synthesis. The same netlist we give as an input to the physical design tool, right. And the cells that are in this netlist, those are standard cells or cells picked from the technology libraries, and therefore, to comprehend a netlist, we also need to give the library, the technology library that we have used during logic synthesis, and this library is typically in a Liberty format, right. And besides the technology library that was used during logic synthesis, during physical design, we also need some information regarding the physical aspect of the standard cells. For example, what is the bounding box for a cell? Where are the pins located for the cells, right? Why we need this information? Because we want to place these standard cells on the layout, and therefore, we need to know its area, its aspect ratio and those kind of details, the physical details, and also we want to make connections between standard cells using interconnect layers and so on, and to do those kind of design changes, the physical design tools need to know at least a few information about what is how is an standard cell looking like in terms of physical dimensions and other things, right. So, for that we need to give the physical information of the standard cells in some abstract form, typically in a library exchange format, or LEF files, right. So, this LEF file contains information like bounding box for the standard cells, the pin locations, and also a few some information like specific resistance and sheet resistance and those kind of thing about the technology, right. So, using the information of the technology library and the physical library, the physical design tools can compute delays and other things, and also they can understand design rules that needs to be followed while making the layout and and come up with the final solution or the layout in the physical design process. So, besides the netlist and library, we also need to give the constraints. So, constraints defines our design goals in terms of say expected timing behavior or the maximum operable frequency that we want for our design, the environment like how the signals are coming to our design and what is the expected behavior for for the signals generated by a design, those are given in the constraints file, which are typically in the SDC format. So, the constraint file that we used in the logic synthesis step, we can use a same constraint file in the physical design, but with some modifications may be related to the wires and routing and those kind of information which are not existing in the logic synthesis step, but which are which are important in physical design step. So, a modified version of the SDC file that we used in logic synthesis can be used in the physical design step also. Okay. And besides netlist, library, constraints, another the information of the physical design or the intent, our intent of the physical design, meaning that what is the size of the layout that we are trying to make, right? What, because finally the layout that we'll be making, based on that the die will be fabricated and that die will be packaged and put in the chip, right. So, we should know that what should be the die size or the maximum area that the layout can take, and what should be the shape or aspect ratio of the die and so on. So, those information are basically related to the floor plan or what a top level description of the layout or how does the layout look like, the size, the shape of the die, and probably we also need to give, say, a predefined location for some entities. For example, we want this the input pins and output pins or input pads to be located at some few fixed location in the layout, or if we want some block to be at a predefined location, we know that those locations are good for a physical design. So, those kind of information can be given in a floor plan and to the tool, and these floor plans can be given in terms of proprietary format that the physical design tools that we are using that understands. And at the end, what the tool will do is that the physical design, taking these inputs, it will produce a layout which in which all the entities of our design are placed at some location on the layout, and their connectivity is the same as it was in the given netlist, right. So, the connectivity should be same as in the netlist, and the location of the entities, for example, standard shells or bigger entities like memories, macros and so on, those are decided by the physical design tools. So, the important information that is added by the physical design tools are, first, the placement of all the entities, placement, and the second information that is added by the physical design tool is the connections between these entities, and that connections are defined in terms of wires running at different layers of metals and so on. So, defining the connections on the layout, that step is known as routing, right? And this routing should basically honor the connectivity that was originally given in the netlist. So, the major task of physical design tools is placement and routing, and so sometimes this physical design step is also referred to as place and route, right, because the major steps are physical design step are placement and routing, but understand that there are many other things that are done by physical design tools in addition to placement and routing, and those are also relevant. So, now let us look into the major task that goes into, or major tasks that are performed by physical design tools. So, these tasks are shown in this figure. The first step is the chip planning, the next step is placement, then clock tree synthesis, global routing, detailed routing, and then this ECO is engineering change order, and finally we write the GDs. So, these are the major steps that are done in physical design, right. So, we will be looking into these steps in subsequent slides and in much more detail later in this course. But a general in or at the top level understanding of this flow is that with each step more details are added to the design. So, details goes on adding into the design, and what are the details that we add to our design in each of the physical design tasks that we have mentioned here. So, once we do the chip planning, we do a kind of floor planning. Floor planning means that we have decided the locations of bigger entities, and we also add PDN, or what are power delivery network. So, these informations are added by the chip planning step, that is floor planning, the locations of bigger entities and other things, those things are added during chip planning, and also power delivery network is made during chip planning. Then in placement step, what is done? It is the standard cells that are in our design. Those are the locations of those standard cells are defined or determined by the placement. Then once the placement is done, then the clock tree is made, right. The clock tree is basically delivering the clock signals to each of the sequential circuit element, or the circuit elements like flip flops, which take clocks as an input, right. So, the responsibility of clock tree synthesis is to make the structure in our circuit such that the clock signal is basically delivered to all the entities in the design that needs the clock signal to operate. Then this global routing adds global routes to the design. Now, what are global routes? We will see. Okay. A detailed routing basically makes the detailed wiring for each of the net in our design. And finally, ECO step makes some incremental fixes or changes to our design, and at the end of ECO, once everything is clean, we get a layout which can be represented in terms of GDS, and this GDS can be basically sent for making mask and then fabrication, right. So, the top level view is that as the design flow progresses, right, from chip planning to say placement, clock tree synthesis, and to other next levels, more details are added to the design and abstraction level goes on decreasing. Now, let us look into each of these steps in some more detail, that what chip planning is, what placement is, and so on. So, the chip planning step is basically the first step in physical design, and this is a major step. Why? Because when we are chip planning is the planning stage for our chip or the layout. At this stage, we do not have much information, right, about the layout, and therefore, we have a lot of flexibility, meaning that we can put the macros at different location, try out at different location, and choose a optimal location and so on. So, at the chip planning stage, we have lots of flexibility, right, and therefore, the chip planning stage has a lot of impact on the final QR that get out of a design, right. So, if we take wrong decisions during chip planning stage, all our following steps or following tasks in the physical design flow will get impacted. So, at this point of time at chip planning stage, we take major decisions about the layout of our circuit. So, what are those major decisions? So, first of all, what we do is that if our design is big, and our industrial designs are typically very big, so in that case we partition that design into subsystems or blocks. We partition a design into subsystems or blocks, and then we carry out the placement and routing and physical design for these subsystems individually, and then combine the results at the top level, right. So at the planning, at chip planning stage, what we do is the partitioning of our design, and once we have partitioned into major portion, we define the location of this bigger blocks or partition on the die, right. So where at the top, during chip planning stage, we decide the location of the bigger blocks that we have in our design. For example, there will be a CPU core in an SoC, or there can be a bigger macro or a memory block or a controller block, or so on. So big blocks, we say that okay, this is the location for these big blocks. So those are arranged and put on the die, right. So at this level, a lot of manual intervention can be required by the tool, right. The tool may not be able to come up with an optimum solution, and in that case we may be able to tweak these locations of these macros and probably get a better QR. So in at this stage, what we also do is that we decide the location of standard cells on our on the layout, right. So typically we will have numerous standard cells, it can be millions, right. So those standard cells, we need to specify a location on our layout where it should lie, right. So we allocate rows on the layout where we are allowed to, or where the physical design tool will be allowed to put standard cells, right. But we do not decide the location of each individual standard cell. We just say that okay, this is the location of standard cell. Later on, in later stages, standard cells will be placed in that area, but we decide the location of bigger blocks in the at this stage. So for bigger blocks, it is not only the location, but the shapes can many a times be variable or flexible. We can vary shape. For example, we can have a rectilinear macros rather than a rectangular. Rectilinear meaning that it can have a shape of say I, right, or it can have a shape of L, it can have a shape of U, rather than rectangular. The shape of some of the macros which are flexible can be rectilinear, and in the chip planning stage, we can decide the shapes of those macros also. And besides this, we also decide the location of the IO cells or the input output cells on the on the layout, right. So in this case, it is shown that all of them are at the periphery, but it need not be, right. So there are other ways in which input output uh, cells can be placed in different kind of packaging environment. So there may be a lot of flexibility where the IO cells should be placed on the or for on the layout, right. So this so the chip planning stage is a stage in which we also plan our IO cell placement, right. So this is a stage where we say that okay, these are the locations where the IO cells will be there, and from there the signals will be driven to the rest of the circuit. And another major step of chip planning is the power planning stage, right. So we know that when we have a standard cell, for example an inverter, right. Now this to operate this inverter, it needs power supply, VDD and ground, right. So to operate any combinational or sequential circuit element, right, they need power to operate. So each standard cell needs to have say power connection and the ground connection. Now we can have millions of standard cells. Now for each standard cell, we need to deliver power to them, right. Now how to decide the network that delivers power, which typically comes from a few pins in the chip, to entire layout, right, because the standard cells will be spread over the entire layout, and not only the standard cell, there will be macros and other entities which will be needing power. So how we are delivering the power to each of the entity in our design on the layout, that is also done in this stage, at that stage, in the chip planning stage, and that part is known as power planning. So we make in this case power delivery network, right. So, PDN, power delivery network. So, while designing this power delivery network or PDN, what is a critical requirement is that the voltage drop should be within some tolerance limit. We know that if there is a voltage source and from that voltage source the power is going to some standard cell, then on the way there are resistances, right, resistances, and because of that resistance and current flowing through it, the VDD that we apply or voltage that we apply at the pin level, at the input port, that will be dropping, and it will reach the before reaching the standard cell. So, we should ensure that the voltage drop in the power lines should be within an acceptable limit. Another consideration that is important during this chip planning stage is the congestion, right. So, a congestion will highly depend on how we place the blocks or bigger blocks on the layout, right. So, if we put a block in some way, then there may be a region where lots of nets are coming or lots of wires are running through that region, and that region gets congested. That is what is known as congestion. Congestion means basically that in a region, in a given region, lots of nets are running together, right, and close together, and that leads to a congestion, and it can lead to timing problems and other kind of problems and routability problems, right. So, if it is highly congested, then the subsequent design steps like routing may fail altogether, right. So, congestion can cause also timing problem, because if there is a congested region, then routing needs to avoid that region, and as a result the length of the wire will be much longer, and there can be more delay in the other wires, and timing problems can be created. So, during the chip planning stage, some consideration of congestion needs also to be taken into account. So, after we have done the chip planning, then comes the step of placement. Now, in chip planning stage, we have defined the location of the bigger entities only, right, the macros or the subsystems or blocks of the design. But for the standard cells, we have said that we have defined a region. We have not yet placed those standard cells in the given rows of on the layout. So, that step of placement of standard cells is done during the placement stage, right. So, the placement is basically decides the location of standard cells in the design. Now, what is difference between the placement of say macros and placement of standard cells? The problem is in terms of scales, because the macros will be say tens, hundreds maximum, right. So, in that region, it will not be too many macros will have on the layout, right. So, in that case, when the number of the area of macros are or the area of macros is larger, much larger than standard cells, and the number of macros that needs to be placed, those are comparatively less. Now, what about the standard cells? Typically, when we are trying to find placement for the standard cells on the layout, the number of standard cells can be millions, right. And therefore, in the placement of standard cell, manual interventions are very difficult, right. So, the placement step is highly automated step, right. So, we may tweak a little bit of placement when we find some violation, but typically the location of the standard cells are handled by the standard by the EDA tools or the physical design tools. While for the placement of macros, a lot of human intervention can be made, because many things a human eye can see by experience that probably this is not a very good location, and therefore perturb that location of macro, and maybe we can come up with a better solution than machine generated floor planning or placement of macros. But in the placement stage, the automation is the only way, because we have the very large number of entities that needs to be handled. So, when we do the placement, what are the important objectives that the tool must consider? The most important objective is wire length minimization, right. So, that is what the most important objectives is for the placement to minimize the total wire length in our design. So, what it does is that it tries to place the cells, the standard cells which are connected together very close together, right. So, if there is an inverter and there is another inverter which is connected to it, then probably these two inverters should be placed together. And if there is one inverter and another inverter which are totally independent, they are not sharing signals and they are not connected, then probably they can be moved further apart on the layout and we may not get impact the PP, right. So, the wire length minimization can also be a tricky task at the placement level, because at the placement level we have not yet done the routing in the design. Therefore, we do not know exactly how the wires will run on the layout, right. So, placement tool must rely on some estimate of the wire length, and based on that it will do some optimization, right. So, the placement tool needs to estimate the wire length, and based on that it will try to minimize it, and that is a challenging problem because the wires are not yet laid out. The other objectives for placement tool is to ensure that the timing is met, right. So, it needs to reduce the delay of the critical path on which the frequency of the clock frequency of a given circuit or the circuit that is being designed, that depends on, right. So, an important consideration for the placement tool is to ensure that the timing is met or the delays on the critical path are minimized, right. And for doing this, again the tool, what it will do is that if there are cells on the critical path, right, then put those cells close together, so that the wire delay can be minimized, and also the capacitors that needs to be driven by a given gate, that minimizes, and as a result the delay of a given gate can reduce and timing can be easily met. And the congestion can also be considered by the placement tool. Why? Because a bad placement of some standard cells can lead to overcrowding of nets, and as a result it can create timing problem or routing problem or routability problem later in the design flow. So, after the placement, chip planning and placement is done, then a step is done which is known as clock tree synthesis. So, in clock tree synthesis, what is done is that clock tree synthesis basically decides the topology of the clock network, meaning that how the clock network will be structured on the layout, and how the clock signal will reach from the clock source. Suppose this is the clock source, then to each of the endpoint. For example, these are the endpoints and there are the clock pins of the flip flops at this point. How will the clock signal will reach from the clock source to the sinks. Those are the flip flops that where the clock signal needs to be reached, those are known as the sinks that will be using the clock signal, and to make connections and such that the clock signal behavior is more like an ideal clock signal, right. So, clock tree synthesis, also known as CTS in short, is also performs the wiring of the clock network, and it avoids detour, since majority of routing resources is still unused. So, note that in a synchronous design, a clock is a very critical signal. Why? Because all the operations are synchronized by the clock signal. Whenever clock signal comes, flip flops toggle state, can toggle its state, and then that signal propagates and reaches another flip flop and so on. So, basically a clock signal orchestrates all the operation in a synchronous design, right. And therefore, the clock signal is a very critical signal in a synchronous design, and therefore, we give the highest priority to the clock signal when doing routing, right. So, we see during the CTS stage, we have not yet routed the signal of other signals, right. So, we are routing first is clock signals. Why we are because the routing resources are fully available. Till now we have used only the routing resources for power delivery networks, right, how the net power is going from the power source to each of the standard cell, that was decided in the chip planning stage or power planning stage. Rest of the routing resources is still available while we are doing clock tree synthesis, right. So, the clock tree, so the clock tree synthesis can easily avoid the detour on the clock signals, and it is very critical that we avoid these detours and reduce the delay of the clock signals from the clock source to the sinks, right. Now, what are the objectives that the clock tree synthesis tool should consider, right. So, the most important objective for a clock tree synthesis tool is to minimize the skew, right. Now, what is a skew? What is a skew? Skew is basically difference in the arrival time of the signals at two different points, right. Suppose the clock signal was generated at this point at say 0 picosecond, right. Let it be, let the clock signal be generated at 0 picosecond, right, at this point, at the clock signal. Now, as the clock signal propagates through the clock network, it will undergo delay and it will reach the sink at some point of time, right. Suppose this clock signal reaches this sink at time say 10 picosecond for this flip flop, right. And for the other flip flop, suppose there was a delay difference in this path, maybe because of this buffer has different delay and so on. The clock reached here at say 15 picosecond. Then what is the skew between the arrival time of the clock at this point and this point is 15 picosecond minus 10 picosecond is equal to 5 picosecond, right. That is the clock skew. Ideally, what we want is that for an ideal clock network, the clock skew should be 0, ideally should be 0. Why? Because we want that all the flip flops get triggered at the same time, and that is what the assumption was made in the logic synthesis tool, and based on that the standard shells and other things were decided during technology mapping and generating the netlist, right. So, during physical design we try to make our clock network as ideal as possible, and therefore we need to minimize this clock skew ideally to 0, but at least we should clock tree synthesis tool should try to reduce the skew to as low as possible, right. And to do that, what does the clock tree synthesis tool do? The clock tree synthesis tool basically tries to minimize the clock skew by choosing a topology such that it is symmetric, right. If the symmetry of the clock, if the architecture of the clock tree is symmetric, then the chances of minimizing the clock skew is very high, right. Ideally, if it is totally symmetric, then it should be 0, right. The clock skew should be 0. Nevertheless, the skew can be something non-zero value because of process induced variations and other things also. But during design stage, clock tree synthesis tries to ensure or make the clock tree as symmetric as possible to minimize the clock skew. The other objective of clock tree synthesis is to minimize the power dissipation, right. So, the activity on the clock signal, activity on the clock signal is very high, right. So, for example, if I take a clock signal, right. So, in one clock cycle it will have one rise and one fall edge, right. And whenever a clock signal changes from 0 to 1, the capacitances associated with the clock tree, right, those will be charged from 0 to 1, and when it goes from 1 to 0, then those will be discharged, right. So, there is a continuous charging and discharging of the capacitances on the clock network, and that leads to power dissipation, right. So, the clock tree synthesis can consume power in the range of say 40% also, right, of the total power dissipation in a circuit. So, the clock network contributes highly to the power dissipation or significantly to the power dissipation of the entire circuit, and therefore, the CTS tool must consider minimizing those power dissipation using some techniques. And typically what these CTS tool do is that they insert clock gators, meaning that they say that okay, in this condition I don't allow the clock to propagate. Why? Because maybe the clock signal is not required for a few clock cycles or whatever may be the reason. But the clock tree synthesis tool will try to minimize power in the clock network using some technique. Then after we have done the clock tree chip planning, placement, clock tree synthesis, then we do go for the routing, right. So, what is routing? Routing is basically it creates wire layout for all the nets other than the clock and power supply. Why other than clock and power supply? Because for clock we have already routed that during clock tree synthesis step, and power, because the power supply the routing of the power nets was already done during the chip plan, right. So, for the other nets that are there in our design, and those will be a huge number of nets, right, because in the if a multi-million gate design, there are lots of signals or lots of logic gates, and those will be connected, right. So, there will be many nets which are still unrouted, and those will be routed during the routing phase, right. And while routing, it needs to satisfy some constraints. The constraints may be related to delay or wire length or some measure, right. So, the objective is to minimize wire length. Typical objective of a routing algorithm is to minimize wire length or routing area or the number via count, right. So, these can be the objectives. Also, the other objectives could be to minimize delay or improve the maximum operable frequency for a given circuit, right. Now, this is a routing is a very complicated task. Why it is complicated? Because there are too many nets, right, that needs to be handled by the routing tool, and it takes lot of runtime, maybe hours or even days to complete a routing for a complicated chip, right. So, since this is a very complicated step, what we do is that we decompose this routing step or break this routing step into two steps. The first is the global routing step and the detailed routing step. So, we decompose the total routing step into two steps, global routing and detailed routing. Let us look into each of them, what global routing is and detailed routing. So, global routing is basically the planning stage of routing. So, in this stage what we do is that we do not create actual wire layout, we are not creating actual wire layout, we are just creating a routing plan for each net in our design, right. So, create the routing plan, what we do is that we divide the entire layout into routing regions. For example, this is the layout of our design, then the routing tool will divide it into rectangular regions, it will divide into rectangular regions, and each rectangular region is known as the global bins, and then the routing tool will decide that if I need to route a net, then how will the routing will be done in terms of global bins or these rectangular regions that we have set. For example, suppose there was a net in this bin and it needs to be connected with the net in this bin, sorry, pin in this bin. If we need to route a net which consists of two pins P1 and P2, which are lying at some global bin here and some global bin here, then the global routing tool will say, okay, for this particular net, follow this path in terms of global bins, meaning that from this go to this bin, then this bin and this bin. So, actual routing is not done, it is just planned that for routing this particular net, I will go through these global bins, right. So, this is a kind of a planning stage for the routing step, right. So, we can take an analogy that suppose we need to decide that we have to go from say Delhi to Calcutta, right. Now, for going from Delhi to Calcutta, we may decide that okay, from Delhi first we go to say Lucknow, then to Patna, and then from there I go to Calcutta. So, this is just one way in which a person can go. So, this is a very top level plan, right. So, that is the what global routing is. Then comes that okay, now I have to do the planning in more detailed manner. Then we say that from say Delhi to Lucknow, which highway I will take, which cities will take the bypass, and so on, right. So, we go into the details of the path, and that is what detailed routing is, right. So, the global routing is just planning that okay, I will go through these regions, and detailed routing then goes into deciding the actual wires or the layout of the actual of the wires. So, detailed routing decides actual layout of each net in the pre-assigned global bins, and these the global bins was decided by the global routing step, right. So, the detailed router decides the actual physical interconnections of nets by allocating wires on each metal layer. So, we have discussed earlier that interconnects are in layers, and we can go from one layer to another layer using vias, right, using vias, and then the wires can run on the metal layers, and then those can be used to make complicated connections, right. So, those complicated layout or the connections through various layers of metals and through using vias, those are decided by the detailed route. So, once the routing is done, basically our implementation is done, right, from once we have done chip planning, placement, clock tree synthesis, global routing and detailed routing. Once we have done the detailed routing, basically our implementation of design is done. Then if there are some problems on something needs to be made changes that we find in the verification step, that this thing is not working as per required or some new requirement emerges, then we can make changes in our design, and those are very controlled changes, and those changes are introduced using a method which is known as engineering change order, right. So, this is a method through which we make controlled changes in our design. Why we want to make controlled changes? Because at the last step we do not want to introduce any new bug, right, and that is why we have to be very careful. So, at the last stage small fixes are made to the design. So, and once we are done with those fixes, then our design is completely ready to be sent out to the foundry for fabrication, right. So, then we can get a GDS out of the layout, right. The GDS basically defines the mask features on the mask that needs to be will be taken through photolithography, and then that will be used for fabricating the chip, right. So, the once we have got the final GDS, we take that GDS and ship it to the foundry for fabrication, right. So, this task of dumping the final GTS and sending it to the foundry, this is typically known as tape out, right. And this is an occasion for celebration for the design team, because it ends an arduous design implementation phase, and then it goes to the fabrication part, right. So, it completes the design part, right. So, a few things that needs to be noted regarding physical design are that between. So, we have in this slide we are showing only the major steps of physical design task, right. Between these steps we can have optimization steps. So, between each physical design task there are optimization steps, small changes in the design to improve the PPA. For example, we can insert buffer for on long wires to improve the delay, or we can make other changes of or make or change the location of the buffers or the size of the buffers for a nets and so on to improve some PPA measure. or we can change the size of a given cell, right? So these are a few examples of what optimization optimization steps can do. They can do buffering, they can change the resize the cell of, it can increase the size of the cell if want to improve the performance, or maybe to meet some slew criteria or some design constraint, or it can reduce the size of a cell to improve the power or similar kind of, or some goal design, meet some design goal, or it can change some placement location to optimize the timing, right? And it can also do some changes, minor changes to the routing to improve the some QR measure like fixed timing and other stuff. So these optimization steps can be introduced in between these major physical design tasks that we have shown here in this slide, right? So these changes that are made in, or these optimization steps that are undertaken in this in the physical design flow, those are incremental refinements to the design. We try to make only incremental changes. We don't want to make very large change in these optimization steps. Why? Because if we do the very large changes, then it can create large disruptions in the design. Maybe we are improving PPA measures for one portion of our design, while the other portion of our design is being their PPA has got bad, right? So it may be that the improvement that we introduce it creates a large, very large disruption in the design, and if we keep on making large changes, we may not be finally able to converge to a solution, right? So therefore, in these optimization steps, typically small changes are made, right? So that only a targeted optimization is done in targeted region of the layout, not in a very large region of the layout, or not a very big optimization steps are, or not a big optimization task are introduced in between these tasks. The other thing that we need to consider is that when we are doing physical design implementation, we also need to do verification for timing, power, signal integrity, and many other things, right? And once we do this verification, we may find problems, right? So and those problem needs to be fixed, right, by making changes in our design, or do something, right? And this achieving this design closure means that we have achieved a state in which everything is fine, right? We have, in terms of what the properties that design should satisfy, those are being satisfied, and we say that the design closure has been achieved. Now achieving design closure is challenging because design tasks that are done, for example chip planning, placement, clock tree synthesis, they are working at a higher abstraction level, and based on that they are taking some decisions. For example, when we are doing placement, right, the placement tool is trying to optimize the wire length based on the estimates of the wire length. It has not yet laid out the wire, right? So those estimates can go wrong, right? Because whatever the estimate was made by the placement tool, in the later when the detailed routing was done, probably that wire got detoured, and a wire length increased by a lot, right? And as a result, timing and other things can get screwed up, right? So if that happens, then we need to fix those problems, right? And to fix those problems, we might need to go into the previous steps, right? For example, what we have done is that we have done the placement, we have done the clock tree synthesis, we have done global routing. During detailed routing, we found that one particular net couldn't be routed, right, because of some reason. And on analysis, we found that the location of a few cells was creating a lot of congestion, and that the routing resource was all utilized in that region, and as a result of that, there was no the detailed router couldn't find a route for this particular net, right? Now if we find such kind of scenario, then probably we might need to go into the placement step and then fix it, right? So if we are in one design task, we might need to go into the previous design task to fix some problem, and this kind of thing introduces feedback in the loop, and we should understand that the flow that we have shown is from say chip planning to the final writing the GDS. It is not completely linear in one direction. There can be loops and iterations of these steps, and these iterations are required because we might need to retract some of the decisions made by the previous design task. And typically in industrial design, it is very unlikely that in one flow, one push button kind of flow, you will finally get an we are able to close the design or get the required results of the on the layout. There are inevitably iterations in the design flow introduced because of the retracting of decisions of the earlier design processes, right. And therefore, the goal of a good VLSI design flow is to basically try to reduce the number of iterations that we might need to take to close this loop, right, and to get the final answer or final layout that is desired, right. So, we try to reduce the number of iterations in this physical design flow, and there are techniques to do that. For example, if one of them could be a better estimate, right. If we do a better estimate at the previous at a higher level of abstraction, then probably the decisions will be more likely to be correct, and therefore it may not be required to retract. And these days a lot of machine learning capabilities are used in design flows to reduce these iterations in the physical design flow. And not only in physical design flow, the iteration can actually go back to logic synthesis also, right. So, a kind of predictive analysis can be done at the and has value in logic synthesis also, right. So, these are some of the references that you can look into to go deeper into these topics. Finally, to summarize in the last lecture and in this lecture, what we have done is that we have looked into the RTL to GDS implementation flow, right. So, the implementation means that we are making changes to our design. Say from the RTL, we have a higher level of abstraction, then to netlist, which has a lower level of abstraction, and then to the layout, right. So, we have actually made modifications to the design and we have implemented our design, right. But this is only half of the story. The other half is to ensure that the design that we have made, it is actually delivering the required functionality, and it is also satisfying the requirements of timing, signal integrity, design rules and other things, right. And these needs to be verified, right. So, we need to verify that those things that the implemented design is fulfilling our purpose. And also once we have designed it, right, that when that design goes to the foundry, are the foundry able to, or has the foundry made one particular chip defect free? That meaning that the way we have designed, is it a similar replica of that design on the chip or not, right, and that needs to be tested, right. So, we need to account for those testing during the design phase also, and therefore, there are two major steps which we need to carry out during designing step apart from the implementation, and those are the verification step or verification or group of tasks which are known as verification tasks, and the design for testing task. So, these two tasks we will be discussing in the next lecture. Thank you very much.